Hello students, in this session we are going to continue from where we left in the last session. In the last session we have seen the LVDT and now we are going to discuss about strain gauges. So strain gauges are very widely used transducers and we are going to see its classification, working principle and other details of strain gauge. So in this unit we have seen these topics in our regular classes. In our online class we have seen LVDT and now we are going to discuss strain gauge, and then in next session we are going to see the piezoelectric transducer and then pressure transducers using bellows, diaphragms and capsules. So this is the content for unit 2, and as I said for your FAT 2, vibrometer, accelerometer, LVDT, strain gauge, piezoelectric transducer and pressure transducers using diaphragm, capsule and bellows. These are the content from second unit for your FAT 2. So now we discuss the strain gauge. So to start with strain gauges, you know what is the strain? It is a dimensionless quantity, and the same concept of strain we are applying here to measure various parameters. So the resistance changes under the application of force or strain. So that is the resistance. This is the basic principle of strain gauge, used for measurement of force, strain, stress, pressure, displacement, acceleration, etc. So many parameters we can measure using strain gauge. So that is the biggest advantage using strain gauges. It consists of a file of resistance characteristics. File is a material, and I will show you the file also, which is safely mounted on a backing material. So backing material is provided, on this it is mounted. When a known amount of stress is subjected to the resistive file, the resistance of the file changes accordingly. So the resistance of the file will change when the stress is applied. So that is especially a known amount of stress establishes a relation between the change in resistance and the strain applied. The resistance is known by the quantity called gauge factor. So gauge factor is also very important 2 mark question from this session, and we will discuss what is gauge factor also in this session itself. The change in the resistance can be calculated with the help of Wheatstone bridge, and Wheatstone bridge I have explained in our regular classes also, and once again we will see what is Wheatstone bridge here in this session. So strain gauge application, this is the simple retrofitter strain gauge. So here pressure measurement, we can use the diaphragm. So this is the last topic also in our unit, and this is the diaphragm material. On this diaphragm we are mounting the strain. So when the pressurized fluid or pressure acts on the diaphragm, so the diaphragm will elongate. So that elongation will cause the strain in this strain gauge. So that is the amount of the stress applied on this strain gauge, and this strain gauge is attached in a Wheatstone bridge, and the unknown resistance is measured using the Wheatstone bridge. So this is one simple application of strain gauge to measure pressure. And this is the load cell. So load cell, we are going to have minimum number of strain gauges, 4 strain gauges. So 4 strain gauges are mounted on a circumferential area and on circumference of any platform. So when the load applied, the strain also changes in the strain gauge, and that is measured using Wheatstone bridge or any other change in resistance measuring technique. So this is the load cell construction, and load cell is also very important concept using strain gauges. We can build load cell, and this is obviously like a weighing machine. So when the person stands here, directly we can measure the weight of a person using the circumferentially mounted strain gauges. So this is another application. And this is the construction, and here you can see the leads, two leads. These two leads are connected to the foil, and this is the foil material, and this is the carrier, and this is the carrier and grid. So these are the four carriers are shown here, and this is nothing but the grid, and we can measure the grid width in this vertical direction, and horizontally we can measure the grid length, and the leads are mounted on the foil backing material, and this is known as carrier, and it is covered properly, and there should not be any external resistances or external disturbances should not act on this resistance material. And now this is the resistance material, and that resistance material using a Wheatstone bridge. Now the resistance change in resistance is a unknown quantity here, that can be measured using a Wheatstone bridge. So in Wheatstone bridge, three resistances are known resistance and one resistance is unknown resistance. So when we know three resistance and change in the supply voltage, and that can be measured using this galvanometer or voltmeter, and once we measure the voltmeter reading, then we can estimate the Rx value from this Wheatstone bridge. So all are known quantities, and this becomes Rx is nothing but unknown resistance. So unknown resistance can be measured or can be computed very easily using this Wheatstone bridge. This is what we discussed in our regular class, and this is the actual strain gauge. So this is actual strain gauge, the same thing, it is pictorial view. So there are four resistances connected as a bridge circuit. So that's what we have seen in the bridge circuit, Wheatstone bridge. Three resistors R1, R2 and R3 will have known values. The value of the resistance Rx will be unknown and has to be calculated. The value of resistance R2 is adjustable, and a galvanometer has to be set in between the points B and D. The property of the strain gauge depends on the size, shape and electrical conductivity of the conductor used. So this is a simple classification of strain gauges. Here strain gauge are three ways it is broadly classified. One is mechanical strain gauge, optical strain gauge and electrical strain gauges. In electrical strain gauge, we are interested in electrical strain gauges only, and wire gauges and semiconductor gauges. And wire gauges are there in our syllabus. We are going to discuss only wire gauges, and bonded gauges, unbonded gauges and foil type gauges. So these are the three types of wire type gauges. These three we are going to discuss here in this session. Depending on the principle of operation and constructional features, strain gauges are classified under these three groups: mechanical gauges, optical gauges and electrical strain gauges. So this is the mechanical strain gauge. It uses levers and gears to magnify change in length. So that is the delta L. The Hagenberger type of extensometer is commonly used for magnification by using rack and pinion arrangement. So mechanical strain gauges are much larger in size. The accuracy of mechanical strain gauge is normally limited and poor, and mechanical gauges are suitable for specific cases only, such as where sufficient space is available. So it occupies more space. So if you have more space available, there you can go with extensometer, and additional mass of mechanical mass does not cause any error, and point of measurement is accessible for visual inspection. So these are the features of mechanical gauges. So the next one is optical strain gauge. Optical strain gauges use multiple reflectors using mirrors or prisms for magnification purpose in incremental length. So Morphin's mirror extensometer is commonly used for measurement. The accuracy of optical strain gauges is high and independent of temperature variations. So that is the another advantage of optical strain gauge. So for our syllabus, the optical and mechanical strain gauges are not required. Just I am giving you additional information here. We are interested only in electrical strain gauges. Electrical strain gauge uses the principle of measuring the change in resistance, capacitance or inductance proportional to the strain applied. So the bonded resistance type strain gauge is most popularly used, while capacitance and inductance type strain gauge are used for special applications only. So the bonded type resistance strain gauge is widely used instrument, and the electrical resistance of wire changes as function of strain. So that is the applied strain. This change in resistance can be measured by using proper signal conditioning circuits. So in between we need to have signal conditioning units, and that is we have discussed in our regular classes what is signal conditioning and what are the types of signal conditioning, that we have already discussed. And sensitivity is dependent on the type of material used. So theory of strain gauge. So this is the simple principle of strain gauge. The electrical resistance of conductor changes when it is subjected to mechanical deformation. So that is the resistance, when resistance change occurs when there is a mechanical deformation in the material. So the resistance of conductor R equal to rho L by A, where L is the length of conductor, A is cross sectional area of the conductor, rho is the resistivity of the material that we are using here. Differentiating the above equation, dou R by R equal to dou rho by rho plus dou L by L minus dou A by A. So just a simple differentiation, and the area is related to the square of some transverse dimension, that is diameter, denoted by D. So dou A by A equal to 2 dou D by D, and therefore dou R by R equal to dou rho by rho plus dou L by L minus 2 dou by D. So this is the final equation, change in resistance. And we have very important concept here, so that is gauge factor. It is defined as the ratio of per unit change in resistance to per unit change in length. So this is a very important 2 mark question also. So this is simple equation for gauge factor. G equal to delta R by R divided by delta L by L. So that is equal to delta R by R divided by axial strain. So dou L by L equal to epsilon A, so that is axial strain, and dou D by D, so that is lateral strain, epsilon L, and the Poisson's ratio here is dou D by D divided by dou L by L, so that is a negative factor here. And when you substitute this V in the gauge factor equation, so the gauge factor will become G equal to 1 plus 2V plus dou rho by rho divided by dou L by L, or we can write this equation. So this is the gauge factor final equation, and G equal to 1 plus 2V plus dou rho by epsilon A. So epsilon A here is axial strain. So axial strain, in terms of axial strain, we are defining this equation, and one is the resistance change due to change in length plus resistance change due to change in area, that is 2V, and here resistance change due to change in resistivity or piezoelectric effect. So piezoelectric effect we are going to see in next session. So that is R change in resistivity or change in piezoelectric resistance effect. So both are one and the same. So the gauge factor is the value of the resistance of the gauge, and its gauge factor is specified by the manufacturer. So this is the value that will be given by or supplied by the manufacturer of strain gauges. If resistivity rho does not vary with strain, so strain is neglected, for a typical value of V equal to 0.5, gauge factor equal to 2. So these are the specifications given by the manufacturer. The strain E usually measured in terms of microns. 1 micron is equal to 1 micrometer divided by m. So this is the microstrain, 1 microstrain. And the resistance wire strain gauge. So there are three types: bonded strain gauge, unbonded strain gauge, and foil type strain gauge. So these three we are going to discuss here. The first one is bonded type strain gauge. The strain gauge is bonded on the surface of specimen, being tested by using thin adhesive cement. So we are just attaching this to the specimen using some adhesive cement. The strain gauge is grid of fine resistance wire. The wire grid may have shape of square, rectangle, or even circle or rosette type. So these are the different shapes we can have in bonded type. And the surface area of the wire section is kept larger than its cross sectional area to avoid stress relaxation and slippage. So here the surface area of the wire section is kept larger. So normally it is kept larger to avoid the relaxation, stress relaxation or slippage. When you have stress relaxation, there will be we are neglecting the stress. So there should be stress that is applied on the material should be taken into account. So that's why there should not be any slippage. The wire gauges may be fabricated in 4 basic varieties, that is flat grid, wrapped around, single wire or woven type. So the wire grid is mounted on a backing paper. So next, unbonded strain gauge. Unbonded strain gauge is just a filament. It is a free filament, a filament sensing element, which is where strain is transferred to the resistance wire directly without any backing. So we are not using any backing material here like we used in bonded type. The number of loops of high tensile strength resistance wire is wound so that the winding experiences an increase or decrease of stress for a given force input. So this is unbonded. It is a free element. And then unbonded strain gauge advantages: because of its radial symmetry, spurious transverse forces are cancelled. So whatever transverse forces they are acting on the backing material, so they are cancelled here because no backing material here. Very low hysteresis and creep, and force summing and force sensing components can be integrated. Disadvantages: problem of fixing at place of measurement. So we are not using any backing material, so fixing is also a problem. And applications: unbonded strain gauges are used in displacement transducer, pressure transducer and accelerometers. Next one, foil type strain gauge. So here the foil gauge uses very thin metal foil of larger area compared to its cross section. The foil is used as sensing element. The foil can be easily fabricated in different shapes such as circular gauges, diaphragm gauges, spiral gauges, rosettes by using photo etching process. So it is a type of attachment using photo etching process. So advantages of foil type strain gauges: higher heat dissipation capability because of large surface area, better thermal stability, excellent strain reproducibility because of photo etching process, more flexible as foil is very thin, available in different shapes and sizes, convenient for measurement of localized strains. So that is the biggest advantage. So characteristics of foil type, typical foil type and wire strain gauges. So gauge factor is approximately 2. Exact value is supplied with the gauge. So manufacturer will provide this. And gauge resistance, standardized values 120 ohms, 350 ohms, 600 ohms, 1000 ohms are employed. Linearity is plus or minus 1. percentage up to 4000 micro strain, and within plus or minus 1% up to 10,000 micro strain. So that is denotes micro strain, and 1 micro strain equal to 0.0001 percentage of strain. So that is micro strain. And the breaking strain is about 25,000 micro strain, and fatigue life is up to million strain reversals. So 10 million strain reversals, and temperature compensation should be provided, and it is we are going to discuss temperature compensation of strain gauges also. And gauges may be obtained with coefficients of thermal expansion that match general purpose steels, stainless steels, and aluminum alloys. Compensation for thermal effects may also be obtained the use of bridge circuits. So bridge circuits are used for compensation purpose. So this is temperature compensation. The strain measurements are to be carried over a long period of time. Therefore, gauges are subjected to change in ambient temperature. So ambient temperature is definitely acts on the strain gauge material. The variation in temperature causes change in resistivity, and ultimately the apparent strain also changes. The effect of change in ambient temperature delta T is given by the simple expression here. So delta R by R to the base delta T is equal to alpha S minus alpha G into capital G, that is gauge factor, plus beta into delta T, and here alpha G is the coefficient of linear expansion of gauge material, and alpha S is the coefficient of linear expansion of specimen, and beta is the coefficient of resistance of gauge material, and delta T is the change in ambient temperature. So this is the temperature compensation expression. So temperature compensated gauges. The temperature compensated gauges consist of elements of two different materials. The dimension of each material are so chosen that the change in resistance of one gauge due to temperature is compensated by other gauge. So that is why we are using two different materials, and this results in minimum apparent strain due to change in temperature. So the temperature compensation using two different gauge material is useful for limited range of temperature and strain levels. So compensation through bridge arrangement. So we can compensate the strain using bridge arrangement also. The temperature compensation can also be achieved by placing strain gauges properly in Wheatstone bridge. An ideal strain gauge is exposed to some temperature variations by placing in the adjacent arm of bridge. So better compensation can be achieved. Such compensation techniques is widely employed in strain gauge instrumentation. So the compensation techniques also should be employed in precise measurements where strain gauges are applied. So this is how we can compensate the temperature also. So for references, you can use these books: Mechatronics by Bolton, and another one is A.K. Ghosh, Introduction to Instrumentation and Control. So this is another very good book, so you can follow. In next session we will continue with piezoelectric transducer students, and we stop here. Thank you.